Good evening, and thank you for the invitation back to talk to BADAS a second time. So, legacy of the Hubble Space Telescope. I wrote this originally on its 25th birthday, but now, of course, as was noted earlier, it's basically hitting its 30th birthday. So it's quite an old lady in many respects. And very few people, especially astronomers, but very few people generally can fail to recognize the iconic Hubble Space Telescope. And that's part of what this story is about. Not only the telescope itself, but the fact that the public is along for the ride. It's not just a scientific instrument. It's not just an instrument for astronomers. So I'm going to take you on a little introduction as to why we need a space telescope. A little bit about the background, how it was built, how the mirror was flawed, how they installed optics to fix the flaw in the mirror. A little bit about what it's done for us, but arguably 30 years of the Hubble you can't possibly get down to a mere 3 or 4 hours that I'm going to take of your time this evening, and a little bit about how the public is along for the ride, and then I will wrap up and just have a little bit of a future look, returning to, do we need more space telescopes? So this is a reminder of the various sizes of space of telescopes generally, and space telescopes are down in this corner. I've forgotten that laser pointers don't work too well on TVs, do they? So in the bottom left-hand corner we have the space telescopes, and these are just the relative sizes of lots of telescopes. Far top left, if you can't read it, is the Yerkes Observatory, and then below that is the Hale 5-meter telescope, one of the largest telescopes of the last century. And over on the right-hand side we can see the size of the proposed European extremely large telescope of order 40 meters or so in diameter, and the space telescopes are down here on the bottom left-hand side. So I'm talking mainly about the Hubble Space Telescope, but also in that box we have the James Webb, which I'll say more about later, Gaia and Kepler, and again I'll return to those other 3 telescopes a little later in the talk. But this just reminds you that the size of the Hubble Space Telescope mirror is tiny compared to, well, it's actually the smallest thing other than the Yerkes lens in the very top left-hand corner. Compared to every other telescope there, the Hubble Space Telescope mirror is actually quite a bit smaller. So, of course, telescopes have come a long way in 400 years since the largest refractor there on the left-hand side, the 1-meter or 40-inch Yerkes. On the right-hand side, the 5-meter Hale telescope. And of course, telescopes have evolved over those 400 years with a desire to get larger and larger lenses originally, but now larger and larger mirrors. Because if we have a larger mirror, we can not only collect more light and hence see fainter objects, but we can also get higher resolution. In other words, we can see either more detail, we can see smaller objects, or we can see those same objects at a greater distance. So it's a double whammy. If we have large mirrors, then we can see faint objects and we can see small objects. And if we look at how telescopes have developed, one of the largest mirrors of last century, the Hale 5-meter, was a monolithic mirror. It was made out of a single piece of glass, whereas now, for instance, if we use the Keck as one of the examples, they are multi-segment mirrors. Each segment is about 2 meters or so across, and the Keck 10-meter is built up of a number of these segments. And indeed, forthcoming telescopes like the European Extremely Large Telescope, again, the segments aren't that much larger, you just have more of them to build up a bigger mirror. So if you have plans for much larger telescopes than the Hubble Space Telescope, why do we bother with the expense of putting one of these into orbit? Yes, larger mirrors do indeed collect more light, but everything on the ground is going to be limited by the fact that you're looking through the Earth's atmosphere. If you're on top of a mountain, you have less atmosphere to look through, so that's a good start, but you're still looking through the Earth's atmosphere. The Earth's atmosphere is turbulent, and therefore you will never achieve the full resolution that the telescope is theoretically capable of. You will still be collecting a large amount of light by having a larger mirror, but you won't get the resolution. And for the Hubble Space Telescope, that lack of resolution, if we were to put a telescope the size of the Hubble on the ground, its resolution would be something like 10 times worse from the turbulence of the Earth's atmosphere. And the 2.4 meter diameter of the Hubble telescope is not entirely arbitrary. When it was designed, it was simply designed as the largest thing that would fit inside the cargo bay of the shuttle, which was the only way of getting it into orbit. The Hubble isn't particularly heavy, it's only about 10 tons or so, but physically it is the largest thing that can fit into the cargo bay, and that determines the 2.4 meter diameter. It would have been nice to have had a larger telescope, but it wasn't practical. So where does it all start? 1970, earlier than you might think, is where the Space Telescope story started. That's when NASA said, wouldn't it be a good idea to have a large telescope in space? Notice that's even before the Apollo program has finished. This is just a year or so after the first moon landing. NASA were already looking forward to, let's do something rather radical. Let's put a big telescope into space. That was the first milestone, 1970, 50 years ago. So we think of the Hubble as being 30 years old, but you could argue it's actually 50 years old, because that's when Space Telescope idea started. That was the first landmark. What do you think the second landmark, second milestone on the story of the Large Space Telescope? Nope. Finance, yes. The second milestone was it was cancelled. Okay, so 1974, Congress withdrew all funding, saying, great idea, guys, no way we can afford that. So funding was pulled and it was basically ditched. A little bit of an outcry. A number of scientists lobbied the senators. There was a serious letter-writing campaign. Yes, that's how serious it was. They wrote letters to senators saying, you can't do this, you can't possibly cancel. And eventually, Senate agreed to a reduced level of funding to get the system off the ground. But basically, NASA were told, if you're going to do this, you're going to have to do it with a partner. So ESA came on board. So we tend to think of the Hubble Space Telescope as being a NASA telescope, but it isn't. It's a NASA/ESA telescope. Okay, NASA were putting in more money than ESA, but it is an American-European joint venture. So in 1978, it was agreed that the Large Space Telescope would go ahead with NASA and ESA funding. And the contractors were then put out the bid, if you like, put out a tender, and it was agreed that the spacecraft would be constructed by Lockheed and the optics would be built by Perkin-Elmer. Yes, it was considered to be a spacecraft. Although we think of it as a telescope, NASA consider it as a spacecraft with a telescope inside. We would think of it as a telescope with solar panels and a few other things, but strictly speaking, it's a spacecraft, and inside there are optics and cameras and spectrographs, etc. So Lockheed had the job of building it such that it actually worked. The power, you know, the gyros to keep it pointing, the electrical systems, the solar panels to keep it fed with power, etc. And the optics were dealt with by Perkin-Elmer. So 1979, construction of the primary mirror begins, and Perkin-Elmer made the 2.4 meter diameter mirror. They did the usual thing. You take a mirror, you grind it to the right shape, you polish it within an inch of its life, or more like a millionth of an inch of its life, and then you declare and you test and you make sure it's the right shape. And about 2 years later, the polishing was declared to be complete, and Perkin-Elmer said, the mirror is fantastic. What is perhaps not quite so well known is that because the funding bodies agreed that the mirror was absolutely critical to the project, they insisted that there was a backup mirror. So Perkin-Elmer were given the job of making the main mirror. But Kodak were told, make a backup just in case. And when Perkin-Elmer said, we've made our mirror, everything's fine, no need for the backup, that's the point where the work on the backup mirror was basically ditched because it was considered no longer necessary. Up to that point, Kodak had been doing exactly the same thing as Perkin-Elmer, different glass, different polishing, different testing, all side by side, just in case there was any problem with the main mirror. So the Kodak mirror was stopped at that point. It was effectively tested and found to be as good as the Perkin-Elmer mirror, is my understanding. But the Kodak mirror, work on it stopped and it was put into a museum. No need for it anymore. That's 1981. 1983, that was the original planned launch date. That was the intended launch date. But there were a few hiccups along the way. That was around the time that it was decided that this new large space telescope would be named the Hubble Space Telescope in honor of Edwin Hubble. So up until this time, it was simply called the LST, rather boring title. So the Hubble Space Telescope, as of 1983, basically sort of almost ready to go, but there were delays. The launch date was put back due to a few slips along Perkin-Elmer's line. They were basically testing the mirror. They thought everything was fine, but there were still a few delays in getting it installed into the optical tube assembly. There were then a few further delays because of Perkin-Elmer and because of Lockheed, so everything got delayed to about 1986 or so. At this point, the budget for the whole thing, the spacecraft and the telescope, the budget had hit something like $1 billion. So Congress weren't too happy at this. You know, it's one of these things that costs do tend to escalate. So I can't remember what the original bid was, but I think the original bid was, we can make a space telescope for a few $100 million, and it's already reached $1 billion. People are starting to get worried because it hadn't stopped rising at this point. And in 1986, if you remember, that is the date of the Challenger disaster, and that meant no more shuttle launches. So although the Hubble Space Telescope was ready to go in 1986, it couldn't go because of the Challenger disaster. It took a while to get the shuttle fleet operational again, and then there was a backlog of satellites, and the military got prime delivery of their satellites before anybody else in the backlog got dealt with. But eventually, some years later, 1990, which is why we think of the Hubble as being 30 years old now, finally, in 1990, the Hubble Space Telescope was launched into Earth orbit. An estimate of the cost at that point was something of order $2.5 billion. This is before you start adding in maintenance missions on the shuttle. This is just the cost as of this particular point. So American and European taxpayers had spent over $2 billion worth of their money to get this space telescope into orbit. Hurrah. A point about the mirror, a technicality before we say what went wrong with the Hubble. The Hubble Space Telescope design is what's called a Ritchie-Chrétien design. The primary mirror is not a parabola. You might think of a parabola as being the optimum shape for a mirror to focus light from infinity to a point, and that is indeed the case. But the primary mirror in the Hubble Space Telescope is not a parabola, it's a slightly opened out parabola. If you think of the various so-called conic shapes, circles, ellipses, parabola is like an opened out ellipse, a hyperbola is like an opened out parabola. Very similar in shape, but not quite the same. The largest big telescope, the last big telescope that actually used a parabolic mirror, was actually the 5-meter Hale telescope, the 200-inch or 5-meter telescope. Ritchie-Chrétien's design was around when the Hale was built in the 1930s, 1940s, but Hale decided not to be too adventurous and try to make a hyperbolic mirror, because that would have been tricky in the 1930s. So Hale decided to be a little bit conservative, and he designed the 5-meter telescope with a parabolic mirror. Every big research telescope since, roughly speaking, the middle of last century have used hyperbolic mirrors, a different shape, but that's part of the problem. A parabola will focus a point of light from infinity essentially perfectly. A hyperbolic mirror won't. You need 2 hyperbolic mirrors in order to form a focus. So testing the mirror is a little bit problematic, and that's the heart of the problem. So although parabolic mirrors have been around for a long, long time, and they can be tested easily, and that's one example of a superb telescope that stood the test of time. The Hale telescope is 70 years old now and still going strong in many respects. But because the mirror shape is different, that is part of why there was a problem in trying to test the shape of the Hubble mirror. Only when the telescope went into orbit, and a few days later when everything had cooled down and they started to point the telescope at stars, did they realize that something was wrong. That must have been such a gut-wrenching feeling for the people who designed it and launched it to realize that something is wrong. It would not focus. They weren't sure if the secondary mirror was in the wrong place. They tried moving that around, but they could not get the stars to form pinpoints of light. They were hoping on the left-hand side, that's what they were hoping to see, nice sharp points of light. Okay, diffraction spikes, you will always get diffraction spikes through this sort of telescope. But basically each star image should have been a point of light. What they were seeing was something akin to what's on the right-hand side. A lot of the starlight is focused at a relatively small point, but quite a significant percentage is spread into this halo around each point. Noticeable in bright stars, less noticeable, but always there in the fainter stars as well. It took a while for them to really honestly say, well, we cannot get this thing to focus. Every image has a halo around it. I think we have to admit that the mirror has got spherical aberration. It's supposedly the best telescope ever made. It's supposedly the most precise mirror ever made, and yet it suffers from a very basic aberration that was known about hundreds of years ago. So let's just remind ourselves what spherical aberration is. If we imagine, let's just think of it as a parabola. Let's forget the fact that it's actually a hyperbolic mirror. Let's just imagine it's a parabolic mirror. What should happen is that light from infinity should come, hit the mirror, and be focused to a point. That's fine. But light hitting a slightly different part of the mirror is focused to a slightly different position. That's what spherical aberration is. In other words, light hitting all parts of the mirror don't come to the same focus. And if we take the extreme of light hitting the very edges of the mirror, it doesn't come to focus anywhere near the main focus. So if we were to say, where do we put our camera or our spectroscope or whatever in order to get the best image? Well, if we put it sort of in the middle of that mess, then very little of the light is focused to the correct place. If we move it back a bit so that most of the light, the black lines, are focused onto our CCD camera, you can see that light that's coming from the edges of the mirror, the outer part of the mirror, that light is being focused in front of the camera, and hence you're getting this halo. Most of the light focused to a point, but the red shows you that some of the light is actually spreading into a halo. So that is a classic sign of spherical aberration, and although they saw that immediately, it took them a long time to admit that's what it is. They were trying to find alternative explanations. It can't be spherical aberration. We can't have spent $2 billion and put a telescope up into orbit and it suffers from spherical aberration. It took them a long time before they had to admit that was the problem. So that's, remember, is what they were hoping for, nice pin-sharp images of stars. To put it into perspective, what would you expect to see if a perfect mirror of that size were to image stars from the ground, taking into account the atmospheric turbulence? Then you would get that sort of resolution. So they are doing better than that same size mirror if it was on the ground. But if it was on the ground, it would be a damn sight cheaper. We've just spent $2 billion putting it into space, and we're only getting a marginal improvement over what it would be if we simply had a 2-meter telescope sitting on the ground somewhere. So we have a horrible, horrible situation where we have a whole set of optics in orbit, and basically it doesn't work properly. How could you possibly make such a mistake? Well, the tests on the mirror, the Perkin-Elmer tests, said it was the most precise mirror ever made. Its surface roughness was about 10 nanometers or so. And if 10 nanometers doesn't mean much to you, imagine the size of the Hubble mirror being expanded until it was the size of the Earth. Then the roughness, the hills and valleys in the surface, would be of order 3 centimeters or so in size. That's the roughness of the mirror, 3 centimeters over something the size of the Earth. That's the same as 10 nanometers over 2.5 or so meters. It was indeed the most precisely figured mirror that was ever made. But unfortunately, it was the wrong shape. It was absolutely smooth to 10 nanometers, much, much, much less than the wavelength of light. But they made it to the wrong shape. It was off by about 2 microns. 2 microns is substantially bigger than the wavelength of light, so you're not actually focusing all the light to the same place. You're getting some light destructively interfering with other light coming from other parts of the mirror because the light paths differ by more than the wavelength of light. 2 microns is huge, especially when you remember it's smooth to 10 nanometers, 10 thousandths of a micron, but the whole figure is wrong by 2 microns at the edge. How could they possibly get it wrong? They spent years grinding it, polishing it, testing it. How can they possibly get it wrong? Well, part of the reason they got it wrong is because you can't do a very simple test. With a parabola, you just focus a distant object and see if it comes to a perfect focus. With a parabola, that's what it's designed to do, that's what it will do. But with a hyperbolic mirror, you can't do that. A hyperbolic mirror won't focus. You need to have the primary and the secondary, and it's difficult to test both at the same time. So if you want to test the primary mirror to make sure it's the right shape, you put in, if you like, it's called a null corrector. That's a fancy name for an extra lens that will make the hyperbola look like a parabola. It's just a trick, if you like, for the test rig. In order to make the hyperbola look like a parabola, let's put an extra lens in, and then we test it as if it was a parabola and make sure it comes to a perfect focus. So they had a null corrector in their test rig. Unfortunately, one of the lenses in the null corrector was in slightly the wrong place. I've heard different versions of this story, but basically it looks like a washer was in the wrong place and it pushed one of the elements of the null corrector off by whatever the thickness of the washer was, maybe a millimeter or so. They did tests with laser interferometry to make sure that everything was in the right place, but they hadn't noticed that a tiny bit of black paint had flaked off and they were getting a reflection from a surface that was not the surface they thought, and hence they were measuring very precisely the position of this null corrector, but they were actually measuring the wrong surface when they were trying to measure the distances. So they hadn't noticed at the time that the null corrector was wrong, which means every test they did was testing for the wrong shape, and they ended up making the surface of the mirror to precisely what they thought was the right shape, but it turned out to be the wrong shape. Yeah, it's the sort of thing that you think surely they must have done some other test. It was said at the time a simpler test could have been done to double check, but Perkin-Elmer said no need. Our very sophisticated setup with laser interferometers and null correctors tells us that the mirror is perfect. There's no need to do a second test to check. Everything is okie dokie. So what you end up with is a mirror that is wrong in orbit and a perfectly good backup mirror which is sitting in a museum because Kodak were told, don't bother, just put it in the cupboard basically. So we have a very good mirror on the ground and we have a duff mirror up in orbit. So the question is, what do you do about that? Well, the one thing that saved the Hubble Space Telescope is the fact that it was serviceable. It was designed from the outset to be upgradable and serviceable for the next 10 or so years. That's going to be a problem with future telescopes for a reason I'll come back to later. But it was designed to be serviced by the shuttle astronauts. And one option was, well, given that it didn't fit into the cargo bay of the shuttle, do we just bring it down again? We've just put it into orbit, it doesn't work. Do we send another shuttle up, bring it back down, swap mirrors, swap the Perkin-Elmer for the Kodak, and then test it all again and send it back up? That was seriously considered. But the final solution was actually a result of the fact that on the ground they had a second camera. This is a non-flight camera. These are commonly done to check things out. If you're sending some probe to the other side of the solar system, it's not unusual to make a duplicate at home so that if things go wrong with the one you've sent out there, you can double check the one in the lab to see what it's doing. So they had a fully working camera sitting on the deck, which was supposed to be an in-flight check. A non-flight check of what's going on, but they had that sitting there and somebody had the bright idea, well, we know what went wrong. Eventually, you go back to Perkin-Elmer, you find out what went wrong, you realize the null corrector's in the wrong place, and you know precisely how much it's wrong by. You know exactly where the null corrector was and where it should have been, and hence you know that the mirror has been made to the wrong shape, but you know exactly what the wrong shape is. And it's been made very smooth, so it's a very good surface, and it's a very good surface which is the wrong shape. So all you have to do is build into your spare camera whatever extra optics you need to correct for that aberration, just like you would do in a camera lens or in coma correctors in telescopes. If you know there's an aberration present, you simply calculate what do I have to do to the light before it arrives at the camera in order to correct for the aberration that I know is there in the main mirror. So that's basically what they did. They took their existing camera and said, let's modify it so it'll work with that mirror. That means we'll then have a camera that will focus correctly, unlike the images that we saw just a moment ago. But what about the other instruments? The Hubble Space Telescope is not just one mirror and one camera. There's a whole host of instruments. Well, if there's a lot of instruments and we know the mirror is wrong, we can't replace all the instruments at once. We can certainly replace that camera because that's ready to go. We can have that ready in a few months, probably, maybe a year or so. But what about all the other instruments which will be collecting light from the main mirror, which is faulty? Well, they came up with a Swiss Army knife solution, which they called COSTAR, a complex set of corrective optics. Those are the optics themselves. These are after they came down from the space telescope, so these are the real ones sitting in a museum. But there's also a model that gives you an idea of what it's actually doing, because it's a little bit complex to see what's going on the left-hand side. You can see from these coloured arms and the little discs at the top, which are representing mirrors, there are a whole set of arms which can be told to move and put little mirrors into the light path between the telescope and whatever instrument you want, whether it be this camera or this spectrograph or that spectrograph. Each one has a different light path, and therefore you need a different set of corrective optics. And so basically you can build your Swiss Army knife and then instruct it, if you're using this particular instrument, you need the blue arm to come out, and that will then send corrected light to this spectrometer. And if you want to use this camera, you instruct the yellow arm to come out, and that will then produce a mirror which corrects the light and sends it to that particular camera. No need for the camera that's going up that's going to have its own built-in correction, but for all the other instruments that are in the telescope, COSTAR, the corrective optics, will allow you to correct for the known error of the primary mirror. So that's what they decided to send up. No particular pressure, but they'd already wasted, in a sense, a couple of $1 billion getting the telescope up there. The astronauts were then told, please go up and fit COSTAR so that it puts the telescope back to a fully working telescope, back to the original specification that we had envisaged. NASA had asked funding, and ESA had asked for funding to get this up. $2 billion later, they had a little bit of a white elephant, and the astronauts were told, go fit this, and by the way, guys, if it doesn't work, that's not simply the end of the Hubble Space Telescope. If it doesn't do its job and get the Hubble Space Telescope working again, not only is it the end of the Hubble Space Telescope, it's probably the end of NASA. NASA will never be able to get funding again from the American agency, and probably not the European, the ESA would find it difficult to get money from the European agency for any sort of project like this, and regardless of ESA, it would probably have been the death of NASA. The American taxpayers had no stomach for putting more money into this sort of project. So if this didn't work, this is really serious. Not just the end of one project, possibly the end of NASA. So when it comes to installing COSTAR, you have to remember that Hubble is not just a telescope with a camera bolted on the back. There's at least, at any given time, because things have changed with service missions, at any given time there's at least 2 cameras and 2 spectrographs in the back end of the telescope, and these have been swapped out over the years. So cameras are sometimes, you may have heard this, sometimes cameras are labeled wide angle or high resolution. You may have heard these acronyms flying around. Bear in mind that that only depends on not the actual mirror itself. Of course, the mirror is just a particular focal length, but additional optics can vary the effective focal length, and the nominal focal length of the Hubble Space Telescope is about 58 meters. So for those of you who've used cameras where the focal length is usually maybe hundreds of millimeters, and for those of you with Schmidt-Cassegrain telescopes where the focal length is 1 or 2 or 3 meters, bear in mind this is a slightly different animal with a focal length of 58 meters. For instance, the size of the chip on the Hubble Space Telescope, okay, holding it up to a projector doesn't work on a TV, does it? But there you go. There's the size of the chip on one of the later cameras in the Hubble Space Telescope. It's about 4 by 4 centimeters. So imagine that chip at the end of a 58 meter focal length. You can get an idea of the precision needed to point the telescope in order to produce the wonderful images that we're now used to with the HST. There's just a slightly larger version of the cutaway. It reminds you that the optics are actually only a small part of the whole telescope. The optics are only the middle 40% or so. The front 25% is just a lens hood to make sure extraneous light from the Earth or the Moon or the Sun doesn't get into the optics. and you see that a lot of what's going on behind the primary mirror, there's the primary, everything behind that is the various bits of instrumentation. Not just the cameras and the spectroscopes, but also the devices that are necessary to make sure the Hubble points very accurately at the target that you want with very high precision. Why worry so much about spectroscopy? Surely all we want is a decent camera, or maybe two decent cameras if you want a backup. Well, no, spectroscopy is very important when it comes to any research-grade telescope, regardless of whether it's a space telescope or a ground-based telescope. If we look at a star, for instance, we might see a spectrum. If we split that light into component colors, let's ignore the ultraviolet and the infrared just for the time being. A star might have a particular intensity distribution as a function of its color that looks a little bit like that. If the star is exciting a lot of gas around it, then in addition to the star spectrum, we might see spikes corresponding to the atoms of the gases that are in the envelope around the star. And if there's something between the star and the spectroscope, between the star and the Hubble, then some light might be absorbed, and so we might see dips in the spectrum. The important thing is that those extra lines, either emission or absorption, in this particular case, in the second or the third, those lines correspond to particular elements, which we can test for simply by looking in the laboratory. If we were to excite the oxygen atom, where do we see the colors of oxygen? If we excite sodium atoms, where do we see those colors in the spectrum? By identifying them in the laboratory, then when we see the lines in the spectrum of a star or a galaxy, we can then identify what elements are present. So if we were to look at Betelgeuse, we would see a line corresponding to iron. That tells us that Betelgeuse is getting towards the end of its life, because you can't get any elements beyond iron when you're using your fusion factories to go from hydrogen to helium to carbon to iron is the last stop, as it were. So when we see iron in Betelgeuse, we know it's coming to the end of its life. So not only can we tell what something is made of by looking at the spectrum, if we know where the lines should be, because we identify which line is which, if we find that they're all shifted relative to where we would expect them to be in the spectrum, that tells us through the Doppler shift that we've got a source of light which is either moving away from us or moving towards us. So we get information about the chemistry and the physics of what's going on, and we get information about the dynamics of how things are moving, whether it be stars moving around a galaxy or galaxies receding through the universe. So images are very important to tell us what something looks like, but spectroscopy is absolutely vital to tell us what is actually going on. What's it made of and what's it doing, as opposed to what does it look like. So spectroscopy arguably is scientifically more important than simply being able to image something. But in terms of getting the public along for the ride, it's very difficult to convince the public that's exciting compared to an image of a galaxy or an image of a nebula. Let me just take you through some of the confusing time of the first few years after the Hubble went up. You can see the timeline at the top there, starting with 1990 launch date on the left, and finishing with 2020, where we are now at the moment, a 30-year timescale. Let's not worry about what these acronyms mean, other than they are particular instruments inside the Hubble Space Telescope. As a rough rule of thumb, if an acronym finishes with a C, it's probably a camera. If it finishes with an S, it's probably a spectrograph. That's really all you need to know. The third and fourth entries there I've just labeled as gyros and elect. That means gyros need to be looked at and potentially fixed or tweaked from time to time. These gyros are the things responsible for pointing the telescope where you want to go. So if gyros failed, you will not be able to point the telescope and keep it pointing at the object, and then all your cameras and spectrographs become useless if you can't rigidly point the telescope where you want it to be. And elect just means electrical systems, i.e. you've got to get power from the solar panels, and you've got to control that power and feed it to the various instrumentation. The point being, when we had service missions, when the astronauts went up in the shuttle to service the telescope, they, generally speaking, had to either swap equipment or fix equipment. And let's have a look at how that actually worked. So CoStar was designed within a couple of years or so after the fault was diagnosed. We know there's a problem with the mirror. We find what the problem with the mirror is. We figure out what optics do we need to correct for that. We put those optics into a second camera, So the top item is, let's not worry about it, but it's actually a wide field camera number 1. We're going to put up a second camera which has got that fixed, and we're going to put up the Swiss Army knife CoStar to deal with everything else. So camera 1 gets replaced with camera 2 on the first line there. CoStar, the Hubble Space Telescope was not designed to have corrective optics in there. If you want to put CoStar in, you've got to find some space for it. In a sense, you had to sacrifice one of the instruments that's already there in order to fit CoStar. And it was decided that the second item there, which was a photometer for measuring the intensity of light from various objects, that would be sacrificed. Let's keep the cameras, let's keep the spectrographs, let's ditch the photometer. And the photometer was ditched and CoStar was put in its place. The asterisk simply means the gyros were tweaked or updated or given a brush up, and some of the electronics was also given a bit of a tweak. And nothing else was done on that particular trip. When the camera was then pointed at a distant object, lo and behold, it focused as it should. In other words, CoStar and the second camera did precisely what they were supposed to do, and NASA were saved. So the astronauts breathed a sigh of relief when they came back to Earth and realized that the scientists were then happy because everything did what it was supposed to do. Some years later, it was decided that other tweaks were necessary. And remember, technology marches on. Remember, it was launched in 1990, but it was built in the 80s, having been planned in the 70s. So it was ready in the sort of mid-80s, and so by the mid-90s, it's already a decade old, and technology marches on. It was decided that other things can be done. So in Service Mission 2, which was in, 1997 or so, the first 4 bars are left untouched, but it was decided to replace one spectrometer with another spectrometer. Let's not worry about what the initials actually stand for. They simply upgraded the spectrometer and replaced it with another one because it's basically 10 years of technology have moved on. So both of these are replacing spectrometers with newer versions of spectrometers, and let's not worry about the acronyms. And then Service Mission 3 was split into 2 parts. In the first service mission, just before the year 2000, gyros needed another tweak. One of the gyros failed and needed to be given a kickstart and a fix. The other elements were basically okay, but the little grey area indicates that something failed. In other words, after that service mission, everything looked fine, but unfortunately, one of the spectrometers failed and was no longer producing the sort of data that it should. And it was decided not long after that to have the second of the Service Mission 3s, the so-called Service Mission 3B, into the early noughties, a little bit of a tweak on some of the electrical systems, a little bit of a tweak on this spectrometer to get it working again. So the grey area is now finished because they basically fixed the problem in situ and got it working again. And the last element here was one camera was replaced with another. Yes, I know it looks like a spectrometer because there's an S on the end. That's the exception that proves the rule. That's actually the advanced camera for surveys. They decided to mess around with the acronyms to confuse people, but that's basically replacing one camera with another camera. Again, more than 10 years since launch, 15 years since it was actually built, so the camera technology had moved on. After the 4th service mission there, things started to go a little bit bad and things started to fail. Eventually, some electronics started to become a little bit less reliable. This spectrometer failed after a few years. That spectrometer was fine, and the advanced camera for surveys, even though it is relatively recently installed, failed after a few years. So remember, we're talking about many, many years here. It's not altogether surprising things fail. They will fail. They're designed for a few years of use, but every once in a while, things don't quite go to plan, and you find that things fail. It was proposed that no more service missions were carried out. In other words, to save money, let's just leave things the way they are. But scientists kicked up enough of a fuss and convinced Congress, please give us one more service mission to fix the problems, and then we hope everything is going to be okay for a while. So eventually it was pleaded and more money was found somewhere at the back of the sofa, and they found enough money in 2009 to have the last service mission, Service Mission 4. Again, it's been quite a few years since that wide field camera 2 was in place. So now technology has moved on, and they now have a camera number 3 with a somewhat larger chip in it and a higher resolution. CoStar is now no longer needed. Note that none of the original instruments are now in place. All of the original instruments have at some time or another in some service mission been swapped out. And each time you swap out, you put in the corrective optics necessary to make sure that camera or that spectrometer works correctly. So there's no longer any need for the Swiss Army knife CoStar. So you can take CoStar out. That's why it's now in a museum, because it was brought back to Earth. And that gives you space for one additional instrument, and they decided to put another spectrometer in there. The asterisks means everything else was given a tweak. Everything else was either fixed as necessary or given a tweak. And so as of 2009, that is it. There's no more service missions. There's no more shuttles. So they can't do any more service missions. I guess you could argue that there are ways of getting astronauts up to that particular point without using a space shuttle, but it's going to be technologically rather challenging to try and do what the astronauts did with the shuttle. And for the last 10 years or so, I'm not sure exactly if anything serious has gone wrong. Nothing has come to my attention as to serious problems. I'm sure there are a few little bits and pieces that are not working quite as well as they should. But on the whole, Hubble is still producing fantastic images and fantastic spectra of various objects. And so it's worked exceptionally well for a little less than 30 years, given that the first 2 years it wasn't working quite as well as it should. Even during those 2 years before the corrective optics were installed, it was still possible to do spectroscopy. Just because you have a slightly blurred star, most of the light is going into a very tight little dot in the middle, and some of the light is scattered around it. If 85 or 90% of the light is going into the central region, that's good enough to do spectroscopy. It's not particularly good for images because all your images look slightly blurred, but it's good enough to do spectroscopy. So even in those first 2 years before the corrective optics were fitted, they were still producing good science. They just weren't producing good images. So a very checkered history, but let's hope that this continues for a few more years. Individual instruments may fail, but as long as the gyros keep going, then it will be able to point at objects and continue to take good data. If the gyros fail, there's lots of them, they have multiple redundancy of the gyros, but as long as the gyros keep going, then it will be possible to point. Once the gyros have failed, and that might happen tomorrow and it might happen in another 5 years, then it will be impossible to point the Hubble Space Telescope reliably at any point, and therefore you will lose the ability to do essentially anything useful with the telescope. That's how it came to be the way it is now. Basically, that brings us up to date to 2020. But what about the legacy? What about understanding the universe? Well, that's going to be tricky in just 5 minutes to give you an account of how Hubble Space Telescope has changed the way we think about the universe. Let me just cover just a few items. The distance scale, exoplanets, galaxy formation, and supernova and the age of the universe. Let me just say 1 or 2 minutes on looking at these various points. This is not the Milky Way, this is our neighbour. This is the Andromeda Galaxy, and we're looking from the core out towards the outer part of the galaxy. Some of these might be foreground stars that we're looking at through our Milky Way, but a lot of these will be individual stars in the Milky Way in the Andromeda Galaxy. And if we look at a particular class of stars called Cepheid variables, whose intensity variation, the period of the variation, tells us the luminosity of the star, by looking, we know that by looking at stars within our own galaxy. If we look within the Milky Way, see what that variation is, we can tell what the luminosity of those stars are. And if we look at how bright they appear to be, knowing how bright they actually are, that gives us a distance scale to Andromeda. And once we've got a distance scale to Andromeda, that's the first rung of the distance ladder in the extragalactic sense, in that that gives us an idea of the scale of the universe. So we can get an idea of how big the Milky Way is by looking at local stars, but we need that jump to a neighbouring galaxy to give us the distance to Andromeda, which was updated by a little over 10%, about 20% or so, when Hubble started taking images of stars in our neighbouring galaxy. So a very important point, knowing how big the universe is. That came within, not within days, but within months, within the first early scientific programs of Hubble. That gave us a good idea of how big the universe is. Hubble was also a pioneer of looking at exoplanets. Perhaps now we're getting a little more blasé about exoplanets. We know about the Kepler satellite, and we know that there are now thousands of exoplanets out there. But in the, what's this, in the noughties, in the mid-noughties, 2005 or so, Hubble was one of the first that actually imaged exoplanets. This is a star called Fomalhaut, and it's a rather odd-looking image in that we've got an enormous amount of diffraction, because scattering, if you like, because the central star is so bright compared to the planets. The central star, we've attempted to take that out so as not to get completely blinded by the starlight. And if we look at what's going on around the star, we find a small blob which moves from 2004 to 2006. There is some object that's going around that star, and that's thought to be an exoplanet around the star Fomalhaut, the brightest star in the constellation of Pisces Australis. So these days we're getting very blasé about exoplanets, but bear in mind, finding an exoplanet means looking for a change of intensity or looking for a wobble of the star, not actually imaging a point of light going round a star. So this, bearing in mind this is 15 years ago, this was absolutely pioneering on the part of the Hubble. Not only to image a planet, but again, coming back to spectroscopy, Hubble actually measured water. By looking at the spectrum, you can get an idea how the spectrum changes when a planet is in front of a star. So you get characteristic peaks in the spectrum, and you can get an indication of whether or not a small planet, like a rocky terrestrial type planet, whether or not there is any water vapor in the atmosphere of that planet. You can get that from spectroscopy. You can't possibly get it from imaging. You can't see what it looks like, but you can get information about the chemical composition of the planet, explicitly the chemical composition of the atmosphere. And again, Hubble was the pioneer to do this because it had the resolution to do this. Hubble, of course, has imaged many, many galaxies. I've lost count of how many thousands of galaxies Hubble has imaged over the years. And by looking with exquisite detail at the structure of spiral galaxies, as well as irregular galaxies, as well as colliding galaxies, we've got a much better idea of galaxy evolution, because we can see so much detail, not only in the nearest galaxies, but galaxies that are quite some considerable distance away. And it's seen various odd structures. You think, well, if that's a spiral galaxy, why isn't it a spiral? It appears to be a spiral galaxy in which the arms are a complete loop rather than the conventional spiral radiating outwards from the central core in the classic sense that we tend to think of as a sort of Catherine wheel, as in the previous image. So understanding structures like this and imaging as many galaxies as possible helps us understand galactic evolution. This image, I think, was quite an amazing one, in that if you look at what's going on here, there's an awful lot going on in this image. Let me talk you through it. There's a couple of very bright stars in the foreground. Let's ignore those for the time being. But in that box, you can see what appears to be a sort of bluish spiral galaxy. And there appear to be 4 yellow dots in it, implying that 4 supernovae have gone off in this particular galaxy. We haven't had one for 400 years. How come they get 4 all at the same time? That seems grossly unfair. But what's actually happening here is that we have gravitational lensing. Although we think of this as a galaxy, actually it's the blue is coming from a distant galaxy, and right in front of that galaxy there's another one. So that orange blob is actually a completely different galaxy sitting in front of the blue galaxy. So what's actually happening is light from a distant supernova is actually being imaged 4 different times. The light is being bent because of the existence of matter, well, more likely dark matter. I said something about this in the talk I gave back in 2016. Dark matter is actually bending the light from a distant object, and because the galaxy is sitting there almost in a direct line of sight, what it ends up producing is 4 images of the same supernova. One way of telling is to look at the spectrum. And if you look at the spectrum, the spectra are identical. There's no way you would expect that from 4 independent supernovae. Not only is it going to be enormously unlikely to happen just by chance, but also the spectra tell you they're actually the same object. But not only that, we have got an image of this galaxy, but by looking at where the dark matter is arranged in this particular cluster of galaxies between us and this distant galaxy, actually light is going a very long way round to get to us as well. So not only is that a galaxy, that is the same galaxy. It's right next door and looks a little bit distorted. It's the same galaxy because, again, light has taken a different route and been bent by the dark matter between us and that distant galaxy. And up here in the top left, that's the same galaxy again. And if you think about the way the light is getting to us from this distant galaxy, it's going the long way round, so it takes longer. So we're seeing further back in time when we see this galaxy via this route rather than via the direct route. It's the same galaxy, but its light is taking longer to reach us. So a long time ago, a supernova went off and has now been imaged 4 times in that image. But the theorists tell us, well, if there's this much dark matter sitting there, we would expect light to take an extra year, an extra 18 months to go the long way round. And so if we watch that other galaxy, if we watch it in a year's time or 13 months or 14 months or 15 months, not absolutely sure, but roughly around then, we would expect to see that supernova go off, because we know it's already gone off because we can see it there, and we know the light via this other route is late by 18 months or so. So let's start watching that galaxy roughly in whatever it's going to be, February of next year. Let's start watching that and see what happens. And lo and behold, they went back to that galaxy, started watching it, and within a few weeks of where they thought, a supernova went off. So that's one of the few times they've ever caught a supernova right at the start of the supernova. Normally, only when it gets bright do you recognize it and then start to record it. In this case, they knew it was going to be happening because of this particular unusual property of dark matter, so-called lensing the light from this distant object, and this extreme case of actually imaging it in advance and then knowing it was going to happen later on. So it's one of the few times they've actually seen a supernova right from the word go, as it were. It would be nice to do the same thing with a much closer supernova, not one that's 500 million light years away. It would be nice to see one, let's say for the sake of argument, 500 light years away. But that's the best we've got so far, and it was predicted because of Hubble's ability to image the same supernova 4 times in that distant galaxy. No other telescope at the time was capable of doing the same. And you've probably seen these images of things like the Hubble Deep Field. Just to give you an idea, that's the size of the Hubble Deep Field compared to the size of the moon. That's how much sky it's looking at when it was told to simply look at a dark patch of sky. I'm told that they had a little bit of a fight to try and convince people that it's worth taking a picture of nothing and spending 1 million seconds exposing a chunk of sky. Let's just point at a chunk of sky for 10 days and let's see what we see. There were so many other things on the list of this is worth looking at with the Hubble Space Telescope. The idea of pointing at nothing in particular took a while to convince, but eventually they did convince the powers that be that it's worth doing that. They pointed at a chunk of sky which is only, as you see, a tiny fraction of the size of the full moon in the sky, just barely 1%. And by doing that, they then realized that, well, actually there's an awful lot out there. They photographed thousands of galaxies in this tiny chunk of sky, and that gives us a good idea of how big the universe is and how populated it is with galaxies. In this particular image, there's a star here, and there's a star in the top left, and I think that's it. I think everything else on that picture is a galaxy, and it gives you an idea of just how much is out there. So it is one of the most incredible images that were ever taken, the deep field in the northern hemisphere, and they also took an ultra deep field in the southern hemisphere as well to verify that everything was looking okay. But the fact that they now have a much better idea of what galaxies look like as you go further and further and further back in time was one of the most amazing and perhaps one of the most unexpected results of using the Hubble Space Telescope. And the Hubble has been able to image lots of galaxy clusters which contain a lot of dark matter and produce these distortions. You can see these little blue arcs which look very odd, but are distant galaxies that have been distorted by the so-called gravitational lensing of the intervening matter, and more likely dark matter, that's producing this particular effect of bending the light as it goes through this cluster and producing these rather unusual arcs. The more you look, the more you see. There's probably 100 different arcs all over that image which give you information about what dark matter is doing within that galaxy cluster. Again, Hubble Space Telescope, one of the few telescopes that has the resolution to see all of these small arcs, which gives you the information about what dark matter is actually doing in that cluster. So scientifically, it's produced an enormous amount which I haven't had time to actually spend time talking about. But more than any other instrument, the Hubble Space Telescope has managed to get the public along for the ride. It's touched the public consciousness, as it were. And there's a quote here from the astronomer: the laws of physics have created these incredible structures, talking about things like the pillars of creation, for instance. And Hubble has revealed them. And through all the research, Hubble has brought the public along for the ride. It's taken excitement that scientists feel with new discoveries and brought it to non-scientists. And I think that's a good encapsulation of how the scientific developments of Hubble have still managed to reach the public consciousness, thanks to the publicity machine that is Hubble Heritage and other web pages such as that. So we haven't got that much time, but let's just spend 5 minutes or so just reminding ourselves of some of the breathtaking images that Hubble has produced, and these are simply some of my favorites. Probably my favorite planetary nebula, the Helix Nebula. This is actually huge in the night sky. It's a fair fraction of the size of the full moon, so this particular image needed a mosaic from the Hubble. It's low down in the south, as seen from the UK, in the constellation of Aquarius, but it is visible from the UK and you can get images yourself. But a beautiful planetary nebula. And one of the things that Hubble has done is image lots of colliding galaxies, which give us an idea, a better idea, of galaxy dynamics. And this one from the antenna galaxies is just superbly detailed. All the pink is new star-forming regions produced by the galaxy collision. Our old friend the Crab Nebula, but seen in so much more detail compared to any other telescope. So-called halo galaxy, which I like simply because it shows the structure of the galaxy. It's almost edge on, but you can see all of the structure in the dust lane. And again, the pink regions are showing you where the hydrogen clouds are, where the star formation regions are. Mystic Mountain, this is part of the Eta Carinae Nebula, unfortunately not visible from the UK. This is visible down south, but incredible structures produced by the stellar winds of the various stars that are embedded in these clouds, sculpting, if you like, these huge columns. And probably my favorite Messier number, M104, the Sombrero Galaxy. Not much in the way of structure, but it's just a beautiful object with that bicycle tire rim around the middle and a huge central bulge. This is a globular cluster, and here it just reminds you that with the resolution of the Hubble Space Telescope, it can see objects right into the core. In most situations, you will overexpose the core, and it's difficult to resolve stars very close to the core, so you tend to look in regions away from the central globular cluster. But the Hubble is able to resolve stars all the way from the edge to the core. And the Milky Way is a barred spiral. The bar is not as large as in this particular example, where the bar is absolutely huge and the spiral arms are coming off a bar which is almost the size of the galaxy itself. Scientifically, some galaxies are very important, and in other cases, they're just amazingly beautiful. And for its 25th birthday, they re-imaged the pillars of creation that were imaged very early on in its career back in the 1990s. They re-imaged it with the latest camera, with the high-resolution camera, the enormous 4x4 centimeter chip that is in the Hubble Space Telescope, producing the now iconic pillars of creation. And again, the Hubble Ultra Deep Field. Again, when you remind yourself that even the smallest dot there is another galaxy, apart from 2 dots, I think, which are stars, you realize that there are thousands upon thousands of galaxies, and the more you look, the deeper you look, the more you see, and that's one of the things that Hubble told us. Just because you don't know there's something there, that doesn't mean you don't look. So it's produced some wonderful images, and scientifically it's advanced our understanding through spectroscopy and images over the last 25 to 30 years. But where do we go beyond Hubble? What's the next step? Surely adaptive optics, where we have ground-based systems in which we can manipulate the mirror, we distort the mirror to try and compensate for the distortions of the atmosphere. That's being done, for instance, by firing a laser into the sky, looking at how the laser wobbles, and trying to change the mirror to compensate for the wobble that we see, because the laser is telling us how the atmosphere is changing. Well, yes, you can do that, but the limit is the fact that you can only see what the atmosphere is doing at one particular point. And it's very difficult to change a mirror the size of, for instance, the European Extremely Large Telescope. You can, in principle, change each segment of the mirror, but generally speaking, it's easier to change a secondary or tertiary mirror and actually distort that. But doing that over a wide field of view is problematic. With the Hubble Space Telescope, you have a clear field of view over the entire region of whatever the chip is that you're using to image the sky. Basically, the image is perfectly clear over the whole chip. If you use a ground-based telescope, you can work out what the atmosphere is doing here and try and correct for it, but it's not what the atmosphere is doing over there or over there or over there. So you can't easily correct the entire image to get anything as sharp as the Hubble Space Telescope, or a telescope in orbit above the Earth's atmosphere. So if you're interested in a particular exoplanet, you can try and work out exactly what the distortion is around that particular star and correct for that. But you won't get a clear image as well of this star or that star or that star. You'll only get a clear image of the star that you're particularly interested in. So there are reasons why ground-based telescopes, even with adaptive optics, will never be a replacement for a space-based telescope. And returning to what I said right at the start of the talk about other space-based telescopes, Kepler, of course, is now essentially retired, but it had a very specific mission to find Earth-like planets orbiting other stars. It did it with a chip substantially larger than the chip in the Hubble Space Telescope. You can see from the size there how large it is. It's not quite coffee table size, but you could probably make a fairly good coffee table out of it. And that looked at a chunk of sky. Perhaps you recognize this chunk of sky, Cygnus on the bottom left, Lyra on the middle right. And it just looked at that same patch of sky. It didn't attempt to survey the whole sky. It just stared at one patch of sky, looking for signs of lights dimming of particular stars, indicating that an exoplanet has transited in front of those stars. It basically just made measurements of star intensities over and over and over again. Gaia is another satellite which has launched and is still producing good work. What is Gaia supposed to be doing? Well, it is measuring intensities, but as much as anything, it's trying to measure the positions of stars as accurately as possible. and it's trying to measure something like 1 billion stars. Not as many as the new Large Synoptic Survey telescope will be doing when it comes online in a few years, but still Gaia will be measuring the positions of something like 1 billion stars to a phenomenal accuracy. Not arc seconds, not milli-arc seconds, but something like 25 micro-arc second resolution. And it will do that by imaging stars over and over again in order to get the smallest errors it can possibly do. It will also do some spectroscopic and photomic, i.e. Photometric measurements, i.e. the intensity, the brightness of the stars, as well as their spectra, as well as their position. The idea being that we'll then have a much better idea of where all the stars in the Milky Way are and how they are moving, so we get an idea of the dynamics of the Milky Way. The first data release from Gaia, they looked at all the star positions and they subtracted away all the stars that were within a given distance from the core of the Milky Way, and then they found that there actually was a little blob in the distance. There's another satellite galaxy on the other side of the core of the Milky Way that's normally hidden by the core, but it's visible. If you subtract off all the other stars, you're left with a few stars in the distance. So it's not just the large and small Magellanic Clouds. There's another satellite galaxy, actually quite a large one, sitting just on the other side of the Milky Way. That's one of the things that Gaia has actually achieved. And ultimately, it will produce a 3D map of the Milky Way. The first data release is out. It will continue taking data for a few more years, and it will release data over the next few years to scientists to do more studies of the Milky Way. How does it achieve such fantastic resolution? Well, again, it's a huge detector, and again, this one is virtually a coffee table size. You can see here the technicians working on it. Again, it's a very large detector, even though it's got a very modest size mirror, just like the Hubble Space Telescope. If you get your detectors right, you can get some phenomenal accuracy. And if we just reflect on the Hubble for the moment, if you excuse the pun of an astronaut and a reflection of Hubble in his visor there, is there a successor to Hubble waiting in the wings? Well, perhaps you already know that, yes, James Webb Space Telescope is planned. It's been planned ever since I was about so high, and they've said it's going to be launching next year or next year or next year, and every year they keep putting back the launch date. I can't remember what it is at the moment. Is it still 2022 or something? So it was supposed to go up in the mid-teenies, 2015 or so, and it's been delayed and delayed and delayed. It's going to be, as you can see here, a segmented mirror telescope. The huge sails on the underneath are to protect it from the heat of any object around, such as the Earth or the Moon or the Sun. And to give you an idea of size, there's the Hubble primary mirror on the left with a diameter of about 2.4 meters, a scale human and a bit, in other words. But the James Webb Space Telescope primary mirror is going to be segmented and will be something like 6 meters diameter once it's all unfurled, assuming it unfurls correctly or unfolds correctly, because you can't fit that in any rocket. You have to fold it up and then send it up to the relevant place that you want to park it. Then you unfold the mirror and then you unfurl those sails to try and keep the heat of the sun away from it. So that's the idea, and the best place to put it is not in Earth orbit, because that would be too close to the Earth and there would be too much infrared produced by the Earth. So you take it to a so-called Lagrange point. L2 is where it's going to be placed. Gaia is already there, so Gaia's at L2, and James Webb Space Telescope will also be sent to L2. This is not to scale, this particular diagram. L2 is about 1 million miles away from Earth. It's further from the Earth than the Moon is. And the idea is if you park it at L2 and put your shields in the right place, you can shield out the Earth and the Sun, and basically you can park it at L2 and it will stay there almost forever. As indicated in this little graphic, it actually doesn't stay at one point. It actually does a little orbit. It's rather weird. It's an orbit around nothing. There's nothing actually at the L2 point. You can just orbit around it. It's one of those weird mathematical results of the way gravity works. But you can see the problem immediately. If you're 1 million miles away from Earth, how are you going to fix it if it goes wrong? If you're in Earth orbit and you're only a few hundred kilometers away from rescue, then if you've got a shuttle or some other means of getting to a few hundred kilometers, then you can, in principle, send astronauts up, fix things, replace things, update things. But if you're 1 million miles away, that's going to be pretty tricky to figure out how to do that. So they have to be sure it's going to work, which is one of the reasons I'm fairly sure that there have been delays, because as they're building the James Webb, they're having to test it and retest it and retest it. They do not want to make the same mistake as Perkin-Elmer and put up a mirror that doesn't work properly, and they do not want to find that the mirror doesn't unfurl correctly, or the sails, the shields, the sun shields don't unfurl correctly. So it's going to be a nail-biting experience to put it up there and send it to L2 and then hopefully get some interesting data from it. And I don't know what they will do if it doesn't work the way that's planned. Why would you want to send up a space telescope which works in the infrared rather than the visible? Well, one of the reasons is, well, we've got a lot of the information we need. That doesn't mean a second Hubble wouldn't be useful, but it's a rather expensive thing to do, build another Hubble and put it up and hope it works for another 25 years. Going to the infrared gives you a different set of information. For instance, if you look at the pillars of creation as imaged by Hubble, that's what you would see on the left if you looked in visible light. You see a whole load of clouds, and most of them are opaque in the sense that there are stars embedded in those features, those columns, those gas columns, and they're being sculpted by various stars. You can almost see a star peeking out the top of one of the columns, but you can't really see what's going on inside. But if you look in the infrared, infrared is less sensitive to the dense regions of these sort of structures and the dust and gas that's there. So you tend to be able to see through them, and hence you can see what's going on. So you can see what's going on inside these structures and get a better idea of star formation. Not only that, if you've got a star and it's surrounded by a whole load of dust that might be forming a solar system, with visible light, it's difficult to penetrate that and see what's going on. With infrared light, you can start to see what's actually going on, what protoplanets are forming, how our solar system's forming around other stars. Not only that, but if you use infrared light, remember, if you're looking deeper and deeper into the cosmos, you're looking further and further back in time, but you're also looking at galaxies which are receding away from us because of the expansion of the universe, and so they're getting more and more redshifted. Most stars produce most of their light around about the visible spectrum. Okay, there are some stars that are brighter in infrared, there are some stars that are brighter in the UV, but a lot of stars, like our sun, produce most of their light in the visible part of the spectrum. So if you start redshifting that means very distant galaxies will look redder and redder and redder. And so if you look into the very great distance, the very distant galaxies are looking very red. And some of them have been redshifted such that most of their light is actually getting pushed into the infrared. So they're getting rather faint if you use visible cameras to actually image what's going on. If you were to use infrared cameras, you would start to see some of these more distant galaxies even brighter than you would see them in the visible part of the spectrum. And hence you can either see those galaxies more clearly, or you can see further in terms of distance, and hence further in terms of how far back in time you're looking, by going to infrared rather than visible. So I hope I've given you a reasonably coherent introduction to why we need space telescopes, what the alternatives are in terms of ground-based telescopes. I told you about how the mirror was flawed and how it was fixed, and I gave you a little bit of a recap of what science we get out of the Hubble Space Telescope and how it has touched the public consciousness. And in terms of the future, James Webb is the future, but we've got other space telescopes up there doing wonderful things as well. Thank you very much for listening.